problem is these things are time dependent. Okay, like let's say if we have construction or traffic jams, then these things vary according to the time of the day and also which day are we in the year, right? So see, based on this, the whole problem is it's very difficult to get this data in real time. Okay, like what is the traffic state of the city right now? Of course, Google Map does it, but Google Map doesn't open it for new vendors to work on it. So that's why what we are trying to do is we're trying to address this problem at a very basic level. Okay, like I never told the model that these are the restaurants which are used for lunch. This is something which is used for dinner. This is something which it came up with the data itself. So we are assuming that if we have enough data, then the model itself could identify that, okay, this locality is always having a traffic jam or this road is always having a traffic jam. And then you should skip this road. And that is with reference to the deliveries happening between a restaurant and a residential area. So if this road is being used, all of these deliveries are going to be delayed. So that's when I'm banking on the model to kind of understand this data without providing it, because providing this data is almost impossible. Like real-time traffic data plus real-time construction data, and then it also has to map to what are the on-ground problems. Like if there is a construction going, that's okay, but what percentage of the road is it blocking? That still becomes a debatable question. So see, all of these things considered together, we try to build the system with accepting as less number of parameters as possible, because if we feed it too much information, then it's also going to go bonkers. Like if in a certain evening, if it's a time where generally you come back from your working place, and in that time period, like 5 to 7 p.m., if we are seeing a lot of traffic jam, then it might recommend going a longer route, right? So frankly, these are something which we don't want to do. In the end, it's not a function of optimizing the delivery time, it's more about optimizing the path taken. So that's why we are banking on these insights being derived from the data, and time will tell if this is correct or wrong. It's just a makeshift solution, so let's see what happens.
Could I just add here, I think Tim had a perfect question there in terms of this bringing the personality of node and the delivery points. It's like the personality, what time of the day it is, what temperature is there around, what is the weather around, how is the traffic, what is the seasonality there. So this is like a personality, right? So yeah. it does make a very great candidate for extension, but as you rightly said, in this implementation, keeping in view of your boundary and scope of the project and what was expected of you, you guys were trying to deliver them the time factor, and that's where that factor and variable comes in, right? Not
and then Ron,
it's more like in an ideal scenario, I would like to even have the mood of the delivery partner in the system.
Yep.
It's not possible.
And then Ron, do you want to come on here? So Ron had a sequence of questions regarding annealing.
Sure. You
can come on, Ron.
Yeah. Hi, Vinay. I have so many questions. Are you, and I'm just going to crank through them. Are you locked into quantum annealing? And is it, I sort of have the understanding that quantum annealing implements certain quantum algorithms a bit more efficiently. And is that why you're staying with that for the moment?
See, not really. So I'll come to that, but see, in general, if you look at quantum annealing, the whole reason why we are with a quantum annealer is because the number of qubits it offers. Okay, so in general, a thumb rule is quantum annealers are simpler to build as compared to a quantum computer in terms of the mechanics, in terms of the electronics, everything. So when we look at a quantum annealer, generally a rule of thumb is it has 10 times the number of qubits a classical computer can have of the similar complexity. So on D-Wave, we have quantum annealers with 2,500 qubits. So getting a quantum computer with 2,500 qubits is going to be a breakthrough challenge. Once we have that, we have like broken encryption effectively. So that's the reason, the primary reason why we are on a quantum annealer. Now, in terms of the lock-in, we only care for the annealing algorithm because that is what is used to optimize this neural network. So the whole option is either we can do this directly on a quantum annealer, or we can use a quantum computer, simulate annealing, and then do the experiment on top of it. So kind of that's the workflow in which we are approaching this problem. We are also trying to work with a few research institutes and build our own algorithm, implementation of the Shor's algorithm, so that it can be used for machine learning training. But so far, we have not seen any progress on that. Because again, the same problem, like every problem statement will have a different quantum circuit that will need different complexities. And if you increase the data, then you will feel short of the number of qubits you have. So that's kind of where it is. So yes, we're on a quantum annealer.
You answered one of my questions. You said you're using about 2,000 bits. And again, since if you're using an annealer, are you using it in a mode where you cycle the annealing process a few times to refine results? And if so, how many annealing cycles do you use per quantum operation?
Right. So, frankly, this is more about how much budget can we afford to blow off on quantum experiments. Like, see, so on D-Wave, if we look at buying quantum time, right, in general, so it comes at a couple of $1,000 every minute, okay, so of quantum time. And that is crazy expensive. Okay, like if you look at like $2,000 for 1 minute of quantum annealing time on a QPU, that is expensive.
So how many shots is that, Vinay?
So that depends on the data size. Okay, so that is anywhere from 2,000 shots to 10,000 shots.
Okay.
This 1 minute time.
But isn't it a little different for the annealing machines? Shots on a
no, see, I'm just
are
following
different. Yeah. Okay.
And see, usually what we do is we talk in terms of experiments and iterations.
Yeah.
Okay. So
and did I understand that you're using the quantum to optimize and accelerate the back propagation of your models?
That's correct.
Is that the only place you're using it currently?
Yep, that's correct.
And so can you give some sort of performance boost in terms of what percentage of epochs you can reduce to get your models trained faster? I mean, are we talking order of magnitude, 2 order of magnitudes?
That's a good question. See, the bigger problem here is, even more than how many iterations can we save, it's a matter of scalability. Okay, like if the model becomes twice as complex, do you need square amount of time, which is the case in classical computing, where if you have something that is 3 times as complex, if you look at a simple neural network, which is 3 times as complex for, let's just consider 2 different experiments, a neural network that is 3 times larger. Now, training this neural network will actually need us to have a cube fold improvement. So a raise to 3 type improvement, which is an exponential improvement. Now, if we look at a classical system of quantum system, then usually what we have observed is this scales linearly. So 3 times the complexity, 3 times the time, not cube times the time. Okay, so that is the most important metric which currently we are optimizing for. And as we scale, we still want to keep this linearity, and we don't want this to go into an exponential mapping. So the answer to your question is, I don't have a clear answer. Sometimes it is orders of magnitude better, sometimes it is slower, sometimes it is a little bit faster, but all summarized together, we want to make it a linear improvement over an exponential.
Okay, I have 2 more. I'm just going to get them in. Have you looked at the area of using the quantum device as a replacement for one of the neural net layers in your model? Complete replacement for it?
Nope.
Okay.
Um,
And then, so my last question has to do with, are you using third-party toolkits for quantum optimization and or deployment? I think you kind of mentioned you're sort of like on D-Wave and you're probably going to be there for a while, so maybe the deployment's not so big. But. Okay. Right,
See, we
thanks.
do use a couple of third-party frameworks, and most of these frameworks now we have customized to our own use case. Like even the D-Wave Ocean SDK, which is their own library to run experiments. We have imported this. We have our own implementation of the same library, and we kind of use that so that it integrates with our cloud pipelines. It integrates with our data pipelines, and we have a full experiment.
Anything else, Ron?
Thank you so much. Yeah, thank you so much. I really appreciate being able to talk with you directly.
Thanks for the questions, Ron. This is probably what a lot of us wanted to hear, Vinay, as far as like the specific details. Now, Dinesh from Meetup said his favorite quantum technology right now is post-quantum cryptography and Cubo. And coincidentally, Lorraine also mentioned Cubo, or I don't know how you say this, in the chat as well. Dinesh, you could come on, or Lorraine, you can come on, or Vinay, you could just keep talking about it.
Yeah, hi, thanks, Kevin. Hi, Vinay. Just have a few questions on the current application scenarios too. So the Cubo part, probably we can just come in on the other on the next round. So the first initial thing is like currently we have all these main applications, whatever running, right? So it's like all sequential and synchronous applications. So apart from that, so whatever we are using for the annealing, whether it's a Fujitsu device or the D-Wave device, so we are just putting we are mostly using the superposition principle in order to obtain solutions at the polynomial time. Okay, so this is one time where we have all the data in place. We just feed in all the data in the parallel execution and get all this resolved, optimized output. So my question is like, how are we going to cater the real-time applications where we have the sequential and consider the banking application or a health application? Like you said, the traffic at least, like for each time for t equal 0, t equal 1, whatever the unit of time, we have kind of a data evolving and we have kind of an parallel multiple data. So then when you come for the banking, or I think it's going to be a user based or kind of an application specific or a process specific. So are we, the industry, the quantum industry, are we going to apply this kind of, how are we going to use quantum in this kind of areas, or the quantum area is like mainly targeted only when we have kind of an higher volume of data in hand?
Very good question. And see, generally, I have an example aligned for this question, so I don't be offended, but my example is we don't try to use a keyboard as a printer. Okay, so that's how fundamentally different it is. And in order to answer your question, see, quantum computing is built for parallel processing. And by parallel processing, what I mean is it's a batch style processing. Like you take an experiment where you have a certain data set, and this data set or a problem statement, or if you consider a quantum annealing experiment, if you have a Cubo problem, Cubo matrix, then the point of a quantum computer is to optimize this matrix and go to the lowest energy state. Okay, that's all that it can do. Now, the next question is, how do you create this matrix, right? So can you do it if you have enough data sets, combining these together and then creating the matrix? Yes, that is a possibility. Can you do this sequentially for every execution of an instance? Let's say we are looking at a banking application. It has to be sequential. Like there is some debit, then there is some credit, then the flow of transactions have to be maintained. So can some sort of Cubo be considered for that scenario? Can you make sure that it runs in a sequential way? Of course we can. The whole problem is, will that be the most efficient use of the Cubo? The answer is no. So in order to efficiently use these Cubo logic systems and run them on a quantum hardware, the whole point is it has to be parallelized, because that's when we'll get the most benefit out of it. We can still run these in a sequential way, but it's not going to give us anything better than a classical system.
Okay, yeah. Thanks, Vinay. So apart from that, I have a question in the Cubo. So the Cubo currently, right? So currently in the industry, I think they are using the linear programming kind of. They have most of the industries are not. They are not using the quadratic unconstrained one till now. So before moving to D-Wave or Fujitsu, kind of based on the annealing techniques, so it's like because it's based on the industry specific. Because if they really have the requirement of a very large data set, then so how the annealing technique, the Cubo kind of in a small, big volume data processing thing is going to target the small application where there is kind of a thing. And second thing, the current linear programming, they have a kind of an verification. Okay, so whatever the output, whatever the optimized output they have currently with the existing linear programming devices, so all they have kind of a verification. For our this D-Wave or Fujitsu, whatever we have currently, so we have to write a kind of a separate uh, optimized functions to manually check whether the data set, what are the optimized output, what we got is correct or not, or kind of how proximity it is correct or not. So is there any way currently in that?
That's also a very good question. So see, currently every other aspect of the ML pipeline, quantum machine learning pipeline, runs on a classical hardware. Okay, like once you do the training and once you have the results, then validating these results is done on a classical hardware. Because frankly, there is no better device to do it, because we need a lot of different types of applications, like pulling in the data, looking at the experiment, seeing the results, and validating the results in a simulated environment. So it's better to do this on a classical hardware. We can do it on a quantum computer, but I think we are just not there yet. So the only point where we use a quantum computer is for every training iteration of a neural network, the gradient descent, we create a Cubo for that equation. And that Cubo is then optimized on a quantum hardware. So instead of calculating the double derivative or going into the math details and then doing the gradient descent, what we do is we do that on a quantum hardware so that it is faster. And it is only faster after the neural network is of a certain complexity. If it is simple to tackle, then my laptop can do it faster than a quantum computer. So in that way, it's more imperative to have a difficult or a large neural network at hand, and then only put it on a quantum hardware.
Okay. And third question is, Vinay, so currently we have this annealing devices like I think Fujitsu offers almost 10,000 qubits in hand currently. So now we design a solution, a very large data set solution currently with this. And in I think now the IBM also they are going to offer in around some 412 qubits or something. So there is a room for the other quantum computing companies to bring in a system with higher number of qubits. So in that approach, when the quantum computer becomes stable, so because the companies they already might be investing this annealing techniques for the better optimization answers or something. So when the quantum computers, the original hardware, when it comes into place with a higher number of qubits, will there be a need to migrate from annealing to a quantum computer again? Because the investment is like a dual investment. So how you think in this way? It's like they have more time, or is like wait for the quantum hardware to be live in coming 1 or 2 years. So what is your view?
See, frankly, I'll tell you, most of this is marketing junk. Okay.
Okay.
I don't know if I should say this on a public forum, but see, the whole point is when we look at any quantum system, okay, only the number of qubits is not the most important thing. Along with this, if we can have a measure of the standard deviation accuracy, okay, like, okay, I have 2000 qubits, but I can measure the output with what certainty? Okay, it's just like SSDs right now. Like you can have twice the amount of storage with half of the speed on the same physical device. Okay, so just talking in terms of the storage is not going to help us. We need storage as well as the speed. So when we talk about annealing, the first point is annealing should always be talked about with the accuracy. Okay, and once we have that, that's the reason we are still using D-Wave, right? Because we also love to move to a 10,000 qubit system on Fujitsu, but we are not getting enough accuracy on all of these qubits. And that is creating further problems. Like, and see, it translates above. Like if you have errors in accuracy on a quantum level, it will go in the ML layer. It will go in the, from there, it will go into the application layer. From there, if you look at the industry application, my delivery partners will start running around more. Okay, even if it's a 2% improvement, and on 100,000 miles traveled, that is still 2,000 miles extra, which is still a very big amount in terms of carbon offset. So it's like self-driving cars. An accuracy of 99.99% means that every one person dies in 100,000 trips. So that is still not enough. You need to get it more than that. So again, coming back to your question, I think we should talk about it in terms of qubits as well as the accuracy. And then in the long-term solution, I don't see we moving away from annealing anytime soon.
Okay, fine. Yeah, thank you very much, Vinay.
And if I could just, add again, Vinay and Dinesh, my point from earlier, it's like having number of qubits versus how to manage those qubits. That becomes your problem if you're not using it rightly and permitting the problem right. So it's going back to square one. That's where exactly you said, if you get that 2% or whatever minimal accuracy more, but spending more, that's the purpose defeated right there.
Very cool. Now, Balaji, do you want to add anything?
I will cover some of them in my PowerPoint. So yeah, I'll take over from there. Yeah.
Okay. Anybody that we haven't heard from? I saw Dave come on.
Yeah.
People
Is it okay to ask a question?
Yeah, go ahead, Philip.
Hi, thank you, Vinay. Amazing talk. I learned so much today. This is one of the best, recent talks here. Given the fact that I was the previous speaker, I can authoritatively speak on this. I have a question. So there was a great report published on the Indian ecosystem, quantum ecosystem, about half a year ago, last February, published by NASCOM and Navasant, that I'm sure you guys have seen. Has there been, I'm interested in this in India in general for personal reasons and for research reasons. So if you have any information on anything new and major that has been published, other than, new articles in the Mint, that I could tap into for more, be very grateful for such info.
For sure. So see, on a company level, we do maintain a database of resources and newly released material. Most of it, so we have a review pipeline only for these materials. Like if something is going to create the next disruption, we want to be on top of it in quantum. That's kind of where we are coming from. So yes, we do have a pipeline to analyze this. And then do I know of anything outside of the report and publicly released materials? I'll have to check and get back on this.
Thank you.
Okay, so maybe see what I can do is I can just put in my email, so just reach out and that way I can get back on this.
Thank you so much.
Very cool. Dave, go ahead.
Maybe I'm sorry, Kevin. Philip, this is Vijay. So in India, kind of alternate to Anila's Quantum Inspired also getting popular. So many startups working on that. I am not guaranteed that it is a commercial grade, but near to the commercial. That is one more advantage going. And second, few research on government, jointly with government sectors and universities and startup. Quantum communication is also getting widely, quantum sensing and communication getting widely popular and attention seeking. Kind of a little progress is happening on that front also. I guess Vinay also can confirm this point.
Thank you very much, Vijay. Dhanyavad.
Yeah, go ahead,
Thanks,
Dave.
Pillai. Vinay, if you don't mind, can you throw some lights on Quantum Inspire? You spoke widely on Anilas.
See, we are currently not actively exploring it, and I'm happy to get back to you on this, because see, I've seen a certain applications pop up, right? But see, when I see any applications, I try to first analyze these with my VC lens. Like, for example, is this something just being done to raise the next round of funds, or is this something which is actually having a material contribution? So some of these applications, as I've seen, they're not really still there. So I'm happy to talk about this more in detail, but frankly, currently I don't have enough data points to talk about it.
Yeah, I'll send over some material.
Sure, Vinay. Thanks. I guess Philip,
Hey, Kevin, you're breaking up. I don't know, is it just for me or everyone?
Yeah, go ahead, Dave.
He was breaking up for me too.
Okay. Yeah, go ahead, Dave.
I think we lost him.
Yes, breaking for me.
He's back.
Oh, okay. Well, thank you, Kevin. And I came in a little late. I was having a meeting with Dr. Faisal Shah Khan, the brains behind Dark Star. That's the D behind me. So we're a quantum startup situated in North Carolina State University. And I would like to thank you for your words of wisdom. I like the frankness that you have there. I want to connect the dots here with Philip, who is the marketer, and Vinay. You've inspired a little conversation going on in the chat. Let me find it. Oh, there we go. So Lorraine. So I like what Lorraine was saying, where Ant-Man had inspired or had tweaked her curiosity about quantum, and I'm wondering if we can encourage Lorraine to tell us a little bit more about that, and then get Vinay to talk about that tech. Lorraine, would you, with your permission, Kevin, can we get Lorraine to say hello?
Yes, Lorraine, go ahead. So everybody, Lorraine was oh, she's coming on. Here we go. Go ahead.
Yeah.
Go ahead,
So yeah. Thank you, Kevin. Thank you for the opportunity to speak again. But this was a very interesting conversation for me, because I'm interested in quantum machine learning, and so one of the first places, because I don't really have a physics background, I heard of quantum computing was from Ant-Man. So when it was mentioned in the chat, it was very interesting to me. I have a background in information technology, and I've been learning quantum computing online through workshops and online courses, and through talks. You also learn interesting things like this one. That's why I'm always up at 3 a.m. to make sure I attend this conversation. So I was just thinking about how they could actually go on Ant-Man and have the quantum community contribute to it with the actual accurate information on quantum.
Yeah, and I think the thing is that it's a multicultural thing. What comes to mind is Worley's Quantum Computing for Babies. So when we start to see this come into mainstream media, nightly news, those types of things, and you could research all these applications, and Vinay's kind of talked about this. The past 2 years, there's an exponential growth in experiments. However, because the hardware is not awesome, the results aren't awesome. So nobody's really hearing too much as far as breakthroughs in medical, all these types of things, breakthroughs. Although, annealing has some with transportation, finance, these types of things. But for the most part, the struggle that we're going through these past couple of years is good because we're learning all these techniques. So when the awesome hardware hits, then we'll be really ready. Say, for instance, if we had 1 million qubits and they were error tolerant and all this kind of stuff today, and we didn't have everything that we've been building up, we wouldn't be ready. So in some sense, it's kind of perfect timing.